So, I guess we start by reviewing material, but in the 3 days of the weekend, probably you would fully remember everything we cover. So, but I would not do a complete review because too many times already. So I just go quickly and then go to continuous random variable. And remember, random variable is you put numbers to outcomes, right? In the random experiment, when the reason is like you can measure the unknown future event by numbers, or you can the number are meaningful, right? So it basically simplify the sample space, like all the measurement. We measure something, it's just like you discard thing that is not important for your cases, and you can use discrete random variable, but you can also use the continuous version, and discrete by means is integers, right? For our application, and for continuous decimal. And just to remind you why we have two versions is because of the math tools is different, right? Discrete allow you to use the standard math in the high school, but continuous require differential integration. So in this class, we do not require math, but the math idea is similar, right? Because the reason of you need complicated math because you involve handling infinity, right? Because very small quantity add together, then we require something very different tools. And just to remind you, for discrete random variable, we have two things: the big P and the big F, right? Big P is ask us, right, what is the value that the random variable can be, and this gives us a probability to equal to that exactly the number. And the big F is the probability that equal to or less than that number. And you can always swap between big P and big F, so don't be an issue for you. And then we also learned that the big P is very difficult to look at. When it's complicated, then you will look at the expectation to simplify it, which is the mean of you repeat this many times, you have number, then you have the average of those. And you can also do the variance, which is also the same as the variance you got from repeating this data. And you have some linear property and also the contrastive property over there. And I'm not going to emphasize, but just to remind you, if you have more than one variable, right, you can just bivariate two numbers to represent the outcome of a random experiment. You can also calculate the sum of expectation and also the variance of the sum, right? Because of the P is very complicated. You can imagine that this become a two-dimensional table, right? If you have more than two, then you have a very complicated tables to record. So when more complicated, we will be using the mean and variance, and the variance of the sum will be more complicated. That would be something that you have to keep in your mind. And last class, we cover all these 5, okay? And also some continuous as well. Not last class, I mean, the 2 class before it. So very quickly, right, just to remind you, Bernoulli, but uniform is just like everything is 1/n, right? Nothing very new, but the Bernoulli is something that is fundamental to all the calculations, right? Bernoulli simply means success and failure, and then you count number of success, and this can be simply the P given by this one, right? And you have the mean is same as P, and the variance P times minus P. And you also have the binomial, which means you repeat this binomial n times, each time independent. So the P function is like this, right? So I explained already. But don't worry, right? Because in application, you just directly put it there. And I also explained to you, hinted that at the end of the day, when N and P N is big enough, maybe more than 30 to 40, and then N times P not too small, then you can use normal. Later you will see normal can approximate this very well. So usually you don't use this directly in the old days, but now of course your computer you can do it directly. But you can also think about this. Actually, a bell curve normal can do things. So the rule will be later you see is n times p and n times 1 minus p is more than 5. You can use that approximation. But we will talk about that when we 2 weeks later. So we have the binomial, we have the mean and the variance. So I think it should be very clear how we'll be able to solve this type of problem, because the example shows you, right? The example, I have the calculate probability here, right? But of course, I can also ask for the mean and variance as well, right? But we didn't put it explicitly. So I would recommend you try to read out the example I didn't cover so that you know what's going on. I mean, as a way to see whether you get it or not. And the Poisson is a special case of binomial where n go to very large, but p doesn't it go to very small, but not go to 0 yet, right? That means p is small, but n is very large. Then you have a simplifying notation there. Okay. And do note that the distinction here is like binomial x is from 0 up to n, but now because n go to infinity, so the number that the random variable can take is from 0 to infinity, right? And here is it's good to measure a number of people arrive, because you don't know before things happen, it can be anything from 0 to a very big number. So you avoid the trouble of binomial. You have to specify what might be the maximum number would come, right? Because binomial is the thing, right? What's the n there? Okay. So the interesting part is the mean and variance the same. So this is a very special thing there. And the formula is like this. Again, you may think this is complicated to calculate, but if your calculator is easy, and also Excel has a formula for that. So we'll talk about that at the end of this whole set of slides. So Excel can do this directly. So this example, right? Model number of people arrive. I think this is sufficient, and then you can do the assignment for that as well. So hypergeometric is very similar to binomial, but binomial is, you can consider, you open a box, the result of first box is dependent on second box, right? So you keep opening many boxes. Each box has probably p that something comes out is success, you call, right? And 1 minus p fails. And each box, the opening or sequence you open, it doesn't really matter. Box 1 same as box 2 and same as box p, right? It will be valid for you do sampling, right? Which will take things to data. Is if everything is dependent, right? When the sample size is very large, then it should be fine. But when sample size is small, potential sample size is small, then this is going to be an issue there, right? Suppose you are going to sample the things that in Hong Kong, then probably it's okay to talk about binomial. But I talk about, say, suppose I try to ask 3 people in this class, and if I ask you, then I can't ask you again, right? So there's a strong restriction to that. Then you should use hypergeometric. And that's why when I said you do quality control auditing, that's always the case. A lot of time, right? You do audit your process. You actually ask this, say, location, you checked it. You can't check it again, right? You randomly check different location, but you can't visit this every day, right? So once you check it, you have the procedure recorded, you can't do it. Or you do quality control, right? You check this machine, whether it work or not, maybe, or check the product, and once you check it, record. Or the product, say suppose a beer or a beverage, you drink it, open it, it's destroyed, so you can't come back again. So we really can't use the binomial. So we have to use hypergeometric. So the formula is something like the combination one. It's not very complicated, right? But it serves the purpose we want. And again, you will later see, actually, it also can be approximated by binomial, because it looks like a bell shape at the end. So when probably you say, okay, everything is binomial, everything can be do normal. Yes, that's true. Almost everything can be do bell curve. And that's why at the second half of this class, basically focus on bell curve. Because bell curve can do almost everything for our level, is when the sample size is large enough, everything become a bell curve. So that's why we're up to here. But of course, when many applications, right, like this, you can't really, it's not big enough. You really can't use bell curve. And we try to model business scenario, then the bell curve doesn't fit very well sometimes. But of course, if you're lazy, then you can just always do bell curve. It's always something that is not too far from the truth. But of course, you want to do something great, then you have to do it right. Then you would want to do the right thing, right? So here is the hypogeometric, this slide. The mean is same as NP. The variance is also NP times 1 minus P, but we have a correction term. The reason is because this is less than 1, the last term, last fraction. The reason is because you keep getting the things. The variation is getting smaller and smaller, right? Imagine you get everything, then there's no variation. Variance is 0, right? Suppose you get everything from there. So that's why you always have a smaller variance there. So I think let's now continue with random variable. And I want to be brief. So again, this example why we don't have P, because when you have a lot of numbers, right? Continuous means that infinite many, there's many. Then this 1 over n is so small, then you disappear. Everything is 0 or close to 0, right? But this one is still no problem, it's 45-degree line. So that's why big F is well defined. Big P is not well defined. So that's why, but you still keep the F. And also we learned that the F contain what we have usually is no problem at all. And for our purpose, as long as the F is a nice shape, it's not, there's no jumping around, okay? I mean, technically it's differentiable, but it's sufficient smooth enough, okay? Then you can always find a small f, okay? And small f behave as if the big P. What does that mean? It means that the area under the f will be a probability. So if I want to find the probability that the random variable less than a, we just look at the sigma f, look at a, look at the left-hand side, look at the area on the left, will be the probability that x is less than a. If I want the probability bigger than a, I look at the area on the right-hand side under f. If I want the area probability between a and b, we just the area under f between a and b. So f is convenient thing, and of course area, if you learn calculus, integration. Okay, so that's why we need calculus. But as I said, our class don't require calculus. If you understand, it's okay, but if not, that's fine. I keep it here because in the future you want to look at a slide and you can see what's going on, and you'll be not surprised you see integration and calculus if you really want to go further. But that will be the case. And also now we have the big F and the small f can do the job to describe the random variable, right? And sometimes it's very complicated. So we use the mean and variance, same as what we've seen. They're just like you repeat these experiments many times, they call numbers, and mean of those numbers will be expectation, and the variance is the variance of those numbers. Okay. So I guess that should be fine, but the formula is like this, but same as what we have seen. So let's go back to this sixth distribution. Don't worry, we will not, we just mentioned the last three just being mentioned because we will not even use the chi-square for our class. We only use the student T and F. Chi-square some uses, but because due to the time constraint, we are not going to cover it. It itself is also very useful itself. But we focus on uniform, exponential, and normal, which commonly you can use it in the real world. Okay, and very often, right, we would try to say something is like uniform between A to B, right? That means what? Anything between A to B going to happen with equally likely, right? And that is what happened when you go to see the news, financial news in the morning, right? They often say what's Hang Seng Index today, and the guy would say, okay, between this number and that number, right? The maximum is this, the minimum is this, and they didn't say about how it looks like. And in general, it means uniform, right? When we didn't specify, and usually that automatically we do uniform. And we explained in detail last class how to do small f and big F, right? If you want probability, then look at the area under small f, and then you also can do the big F idea as well, right? The area under the small f is the big F. And I already showed you this big F, right? Just remember big F, and then the mean and variance. The mean is just the middle between A and B, is the midpoint A and B, and the variance, I really can't say anything, but just a formula. I have the proof there, but I don't have good intuition why this is over 12. But you can see that it's proportional to the range, right? B minus A is the biggest minus smallest. Then get squared. But the 12 is something that I can't really say too much. We do all the calculation there, so please check it out. And also we talk about exponential, right? Exponential is the thing that closely to the horizontal. Horizontal means over a period of time, right? How people arrive. Okay? Number of people arrive in the interval that is horizontal. Okay. And exponential it's not about number of people arriving, but time between each arrival. Time between the first guy to come, to the second and third guy, and second and third and fourth, and fifth and first. And because of the idea of Poisson followed by binomial, right? So the time between first and second and third, they all follow the same. And if you know exponential from physics, that is actually how engineer model the nuclear reaction. How, because the nuclear fusion or nuclear reaction actually is random distribution follow exponential. So it actually is a real application, and it fit very well to model phase happen. Okay. So, and exponential, the reason is because they look like the exponential curve like this. Is the f function initially is very large and slightly down. So that is the most likely it's going to happen immediately, but it's getting lower and lower. But that was the shape, and that's why it's called exponential. Okay, and you will see this is the mean and the variance, and do remind that the mean and variance are have to be very careful. Although this is Poisson, but the time is not the mean and variance is not the same. Okay, and we already show you how you can calculate this, how to apply this. Just to remind you, exponential time for phase to happen. Okay. So that means that it must be positive, right? Things to happen. We can amount is zero, can't go there. So now here we come to the very last one, the most useful thing that we're going to cover. I think this is the thing we cover in this class, and hopefully we can finish everything for normal difference today. That's most important. It's essential for the second half. Course. Bell curve. Hopefully you get it. So for the bell curve is probably you know already. It can run from negative infinity to positive infinity. So that's good because it can be anything. So help us to do a lot of modeling. You don't have to fix what you learned before, right? It's almost positive. Right? Poisson go from 0 to infinity. Binomial is also 0 from n, right? Hypergeometric is also a positive number, right? Uniform can also be negative, but you have to say what is the minimum, right? Here, you don't need to say anything. Okay? Here, by normal, just need two things: mean and area. Tell me the mean, the variance. Mean is the mu, variance is sigma squared. It's the same notation as the first topic one, so that's a good one. And this very ugly formula, I don't expect you to remember anyway, because that's why I put it in the white line of the blue one. So remember this. Why? Because this thing you cannot compute by hand. Always you have to use computer or also paper. And in our class, we can't use computer, the same theater, so you will learn how to do paper. It's very important. Or you have to know right down the Excel button. You may ask, okay, this very tricky question, okay? You may ask, is it very common to see, right? Although it's called normal, right? And if you know the history, this is invented by famous mathematician Gauss. We actually try to study that time when people look at the sky, so the comet, how to arrive, and he used this kind of thing to estimate. Anyway, let's talk about this. And turn out the modern thing to understand is where you see this kind of normal is basically almost everything. Why? We'll talk about this in somewhat hidden in the next topic. After is what we call the most important field in statistics is called central limit theorem, which essentially said if the random variable is sum of the outcome of many different parts, which is random, and at the end, what do I mean by that? look at this, I said IQ, weight, and height. IQ determined by parents, DNA, and how they combine. What do you eat throughout many years? What you're learning for many years, right? All the things that together from the eye. Same as all the weight, all the height, right? What you eat, we're born with, right? Many things, right? The environment, so that is why we see all these values. Same as business allocation, right? Whether people like a particular object and whether they like to win the pay to cut your product, will also likely follow bell curve because it is designed by many people. Whether they have seen your product before, whether their friend like your product before, whether you have good experience, whether your spirit, your mood, or everything, your temperature, weather, many things together, add together. Then that's why application, a lot of things that we tolerate. So that's the reason. So as I said, this is very complicated. You don't have to remember, but at least you need to know the mu and the sigma means, right? You can see the three different lines here, right? You can compare the green one, the red one, right? And the same mean mu 0, sigma squared, the variance is different. One is 4, one is 1, and then you can see the green one is taller than the red one, right? The reason is because this F function, right? That means that the area must be 1. So if I have the red one is more spread out, large variance, you can't have the same height, otherwise the area is not. So why the green one, just like a hammer, will just have damage that and the mu just moving the location. So that's why I compare the green and the blue one, it just move left or right, right? Because whole area must be 1. So just mu is just moving things that move the bell location. So mu is the location of the bell, and how fat, how tall is the bell is determined by the size. Okay, and they are independent. So change the mu, just move location. Change the sigma, just change. So it's very good. Mu and the sigma are not interfere with each other. It's not true for many cases. Why? Okay, remember your binomial. Binomial is the mean is NP. Variance NP times 1 minus P. You change N, it's for variance and P. Change P, you change for variance and mean, right? So you can't really change one without changing the others. Okay, but here it's okay. So I already said this is the normal distribution. Okay, although I put the formula F over there, but you don't have to remember. No way we are in the class using it anyway. I'm pretty sure. Except you go to that class, no one actually integrate that guy. So I don't remember any time in my life actually work with that guy except I write the slide. So I don't see any reason you would be working it as well. So I just put it there in case, because as I said, it's the most important equation, so I can't really not write it. But nevertheless, if you in the exam you don't have time to write anything to cheat sheet, then you just forget about this. You don't have to be too much worried about this one. Okay. And the magnifications, as we said, the first one is like approximation with many things you know very well, binomial, Poisson. Second will be actually very useful things when you learn physics. Third will be if you try to model things in 2-dimensional space. Okay. And imagine physics, you just say there's a center of the atom is here. The electron is run over, right? Then here you say, where is the electron? Only depends on how far from the center, right? The further away is less, but closer it doesn't really matter which location. It's like, say, symmetry based on the distance from the center. That's a radial symmetry. And second is independent of dimension, right? I call this X, this is Y, this is center. It's a plane you see it, right? X and Y doesn't mean that, right? This is just. We call this X is Y, because rotate doesn't mean that. So that's why the independence of 2 dimensions. Or I tell you where the X is, I can't tell you where the Y. I tell you it is the center is here, I tell you is we're close in terms of X, then say anything about the Y. It can be anywhere. Okay? So turn out to be these two properties. The only thing you can have So that's why we're surprising, right? Because you can't have other things. If you want these two properties satisfied, you must be normal. I'm going to show you the proof, but there's a map behind why you see this crazy exponential function work, but that is what it is. And last one I mentioned already, central limit theorem, that arise from very natural process that combine many things together. So what you see is observation is a combination of many things. As long as each thing is independent, normal, then what you observe. So that's why when you enter the college, you take the exam, there's a bell curve. And now we go to research data, we will look at the syllabus, we use the assess criterion-based assessment. So based on how well we do it. Why? Because the bell curve does not time, right? Because you guys are very good enough. So using a bell curve will not be very useful. So the bell, you will need the top in the tail of the bell. So really doesn't follow very well. So doesn't apply. When n is big enough, yes. But for a class like 70 students, doesn't really work. If I have 700 students, bell curve makes it work. Limited number of students here, so I don't think we have to worry about the bell curve. Okay. So here's some math here, but I don't think there's any reason to go over them. There's a proof for what I said. All these things have been proved there, but I don't think anyone will be interested in this. I think the only thing I want to mention is this two things. One is the kurtosis. We mentioned the first topic is the bell curve is straight. Okay, so that's why you always compare the bell curve because bell is normal. So fatter than bell, so fatter than normal, bell is fat. Bigger than bell is big. The bell is symmetric left and right. So the skewness associated. So that's why you always compare this. Because normal is thing you observe. Normal. That's easy. But of course, the original name is called the Gaussian distribution or the Bell distribution. But now, because it's seen so often, so common, that I have a name called normal. And this try to say some application about the way out or the Lexel equation or for actually for normal. If you ever learn I just hint them in this moment. Okay. Now, since normal is so common, we need to give a notation. So we will say a random variable follow a normal distribution with that is nil. Nil is you can read as is distributed as or follow the distribution of n refer to normal, capital N, and the bracket, because there are two things there. One is the mean mu, sigma squared. So that is the standard notation. We use it as shorthand for the rest of our course. So that's the meaning of this is random variable x follow normal distribution with mean mu, sigma squared. Okay, that's the standard notation we're using, and not just us. Look, read every textbook follows it. Not my invention. Okay. So here is something I think that is not surprising, but you will see this is the case. Is remember the mean has linear property, right? So if I forgot to share the screen. I'm sorry about that. I hope it's okay. I'm sorry I forget to share the screen. If you happen to see this, it's okay. I think I didn't go over some things new thing too much. I think it's okay, right? I think it's start from here. It's not. I'm sorry about that. So the linear transformation here is like I have the x, right, like this. That means that the following, right? One thing is from this one, I would know immediately this is mu, right? And the variance is sigma squared, right? You know it already. And the next thing you know it that it must be true is this expectation, ax plus b will be equal to A mu plus B, right? That is what we learned, right? Linear polynomial. And we also know the following, right? Also, the contrary property is variance of AX plus B will be A square sigma square, because B is a constant, so we don't have that. Right? So you know that this true regardless of whether the normal is. The fun thing is, price or not, but the fun thing is you do this, the bell curve, you multiply it and add something, it's still a bell curve. Okay? So first, don't remember, let's say suppose the bell, you move it, it's still a bell. Okay, you may say this is trivial, right? Imagine binomial. You add one, it's not binomial anymore. Horizontal, add one, it's not binomial. Exponential, add something, it's no longer binomial. Right? You add something, no longer follow the old thing. But the good thing about the normal is to add a number, whole thing is still normal. And the good thing also is like we multiply the thing, spread out. Multiply by A. Actually, the mean move by A. And also spread out more. So the variance increased by A squared. So and the good thing is still a normal, which is something surprising because it's usually wrong. Okay? If something follows the standard some distribution, multiply something plus something, usually it's not the same. It can follow the whole thing. But normal, no matter how it multiplied, no matter how it plus, it also be normal. So that's give us a very nice thing, right? You can see why normal so come. No matter how you squeeze it, how you portrait it, how you move it around, still normal. The bell moving. So why this is important? Why say okay? Why we care about moving around? You hammer it, right? You expand it, you squeeze it, right? Like a play doll, right? Like things you want to play around with. Why is good? One of the reason is, remember, you can't really calculate the normal, right? Because the complicated, the F1 is so complicated. Can't really do it. So what does that mean? It means that you have to use calculating. And because each mu and each sigma will give you a different F, right? Then you have how many F you can do, right? So the good thing is that is why we would always focus on one, what we call the standardized norm. You would just focus on only one, which is mu is 0 and sigma squared is 1. That's called standard norm. And there's no problem because you can always convert one to the other. What do I mean by that? Okay, let me write down. Let me write in this slide here so that you would have some idea. Okay. So suppose I have a bell, it's like this. And the bell means this is the mu, is here the mean. Sigma square is how spread out is. Okay. But the normal is like characterized. Okay. It's this F function, right? This shape is the F, right? This is F here. Now consider the following. Okay. F gives us what? Probability, right? I pick a particular point here. I call it, say, A, whatever, right? And I can look at the area, this guy. Okay? This is, I want to look at the probability that X is less than A, right? And how to find it? They use calculated, right? Makes it very complicated those days. And that's why, of course, now you can computer can easily calculate anyway. But actually, what the computer do is actually not doing this. Although you tell him to do this, he will not that stupid to do this one. Okay? He actually have a thing called go back to the standard normal. Okay? How do you convert to this here? This is just basically you subtract the mean mu over the standard deviation. Why? Because this will corresponding to 0 here. Okay, and this is a variance of 1. Okay, and why is it important? Because I can convert A to here. This point is just A minus mu over sigma. Okay, and by doing this operation, I look at this area, which I already know how to do it because I only have one standard normal. I know exactly what our numbers are. So this is something we do. This is called standardized normal. So the normal, even more standard than normal. Because there are many normal. We focus on particular normal, which is mean 0, where we we'll use this very C table. Then the question. I mean, of course, for those of you who have learned this before, that is something too true. I'm sorry about that, but soon, because not everyone have learned it, so that's why I have to be a little bit slower than we say. Okay, standard normal. Okay, I'll do total standardized. Okay, and why we do that? Because when you do the assignment or you do exam theater, you have to look at the table. What we can actually do Excel formula, but and in the F table, usually they give you these two versions. It's the area on the left hand side because they use the big F. You can either have two versions. One is this number is negative. So what does that mean? Because it's symmetry. Okay, so either people would give you the left hand side or the right hand side. Why sufficient? Because symmetric. Right? And let me say a little bit about the symmetry here. Okay. Why symmetric is sufficient? 0 is here. This is Z. It's a bell curve. Okay. The F is a. So suppose I want to figure out this is, say it's negative 2, say, right? I want to have this area. Okay, this is available from the table, right? And now suppose I only know the negative. What happens if I want to know this, right? If I want to know the following. What can I do? Okay. Suppose I want to know this positive 2. Okay, I want to know this value, right? I want to know f of 2, right? But you only give me f of negative 2. Okay, what can I do? Okay, the things you learn from primary school or kindergarten, that's the method. Okay. So the red one is essentially same as this purple one. Same. Okay, so f of 2 is simply 1 minus f of negative 2. Okay, and you can see the symmetric here. F of negative 2 is 1 minus f of 2. Okay. You can always go back. So if you give the positive C table, you can always go back and forth and have fun. Okay, is that okay? So it's symmetric. So let us really have fun and before break. Okay, I think this is important before break. Is try to look at this up. Okay, I want to show you how to look up the first item. What is Z is less than 1.4? Okay, I want to get the 0.9192. Okay, then so actually this is what this means, right? The F function first. So I read this and then we have a break. Okay. So suppose we are going to use a negative one. Well, positive as well. But okay. Remember, we want 1.4. Okay. So we have negative, which means that we look at negative 1.4 and 1 minus. Right? You get that part? In case you don't, let me write down here again, because since this is important, I don't want you to miss it, right? So the question here is, I have z, this is 0. Okay. I ask is 1.4 here. I want the red area, okay, which is F1.4, but I don't have this table. The table I have is 0. I have this guy, negative 1.4. It means I have this guy, right? But this guy, same as this guy. The empty spot, the 1 minus this. This is equal to 1 minus F negative 1.4. Okay? Okay? So I need to look at the table. F, take F negative 1.4, subtract it, it's my answer. Okay? So let's look at it. Okay, and then we have a break. Now, here, how to read this table? You need to read the most left column first. Okay, give you the biggest number, and you look at this, the second. Look at the column. Look at the row first before you go to column. So negative 1.4 is here. Okay, I don't know whether you get it, because you read the row. It's negative 1.4 here, and it's 0.0808. Okay, so that means that you subtract 1 from it. That's how you get this answer, right? Or if you're lucky, you have the positive table. They are done. It just this number. Okay, so that's why if you go to exam, bring more tables to subtract. But if you only bring one, don't panic. Very good. 4 pages, right? Let's see. Okay, is there any question before break? Because on the break, we actually go into this kind of checking exercise, do the normal, because you know how to do this calculation. It's the way that you do a normal. I told you normal so common from this class onward. So let you know how to do it. I hope that's okay. Okay, so as our usual practice, I would want you to do it for me. And since today is our big day, I bring some small gift for you guys. Okay, so enjoy. Let's bring it to you. So I hope you're enjoying the break. So let's see how well we're doing and how well you're doing, and then let's continue. Hence, make sure that you have good mooncake, but don't eat too many mooncakes because it has high cholesterol. But probably, I mean, I will eat the healthy one. It's called a nuts mooncake, and five different nuts together. So that's what I bought. So I'm not going to eat the classical version, the healthy one. Maybe you can try healthier next time. Yeah, happy. Hopefully everyone is happy. Yeah, by no one made mistake here. I guess we are. Oh, it's cloudy. Okay, that's good. And yes, that's very important. The negative, same as 1 minus. The Z table. They're very important. In standardizing, mu is 0. Yes, mu is mu. It's a Greek letter. The mu. The bell curve is very important. Yeah, that's good. I'm glad that you can recall that. And I think everyone agreed it's not too fast. And most of you can still follow. Look at jokes. Where jokes, I hope. What are you going to do? Actually, yesterday I went to the Victoria Park to see the lantern show. I mean, you can sometimes go to the Hong Kong Island, but it's not that a lot, but there's something there. And today I'm going to go home and eat with my parents and my brother, and then eat together with some food and some mooncake. Unfortunately, probably can't see the sky because now it's like so light pollution, so we can't really enjoy it. You can't see the moon from your apartment, but at least hopefully you're happy. And some of you told me that you are working for your midterm, so I hope you spend some time to take a rest. That would be good. Anyway, let's get back to our thing, okay? And I hope I told you how to look at the case. I mean, I illustrate again, what is z less than negative 1.6? Because I have a negative table, I just look at negative 1.6, right? So I can easily check negative 1.6 is essentially this one, okay? So if I really want, 5% is my answer, right? Or I can look at 1 minus 1.6, which is this answer, 1 minus this guy, okay? So regardless of which one you look at, then you will be able to find things that you want, okay? And the next one is slightly more complicated. It's between two values, okay? So the idea of this, you have to rely on what you learn in the kindergarten. Okay. So first is asking 1.4 and negative 1.6, right? So this is the blue area, that is F, right? The blue area is area we're supposed to find, okay? And how to find that? Because with the table, we only know the area on the left-hand side is the big F, right? The big F is given to you. Then we use the kindergarten method, okay? The green area is, we actually found it from the second bullet point. And the red area is, we found it in the first bullet point there. So the difference between red and green is blue, right? Red is found in the one before the break, and the green we have just found, and red minus green is blue, okay? So don't worry about that. We will be doing this all the time. So this is something that you will master from this class, because we keep finding this kind of, I don't know whether it's stupid or not, but this is something we have to look at, okay? All the time, okay? Now, I think this is something that will be very useful, because this connect what we call If people don't know statistics, this is what they learn, right? If you learn, I don't remember, this is something that you also learned, maybe some other situation. It's called the sigma rule or rule of thumb, okay? It's based on the idea that is mean and variance. And the idea is actually based on the bell curve. We often say things, it will be within 1 SD with 7%. That is exactly from this. Okay? Within 1 SD, 68%, 7%. Right? Things within 2 SD is within 95%. Okay? Things for 3 SD is 99. Okay, let me say the application, right? Suppose I tell you, suppose a midterm, right? We don't, but suppose midterm, okay? And then we say the mean of this class is 70, right? And we say the SD is 5, okay? And then you ask yourself, if you get 80 marks, where are you? Right? 80 marks is 2 SD, right? Maybe then it means that you are top 97.5, right? Here in the middle, right? If 1 SD, 1 SD, 1 SD here, this is 68, right? And if you go 1 SD more, 1 sigma more, 1 sigma more, this is 95, right? 95, what is left here is 5%, right? Add together. So it's 2.5 each side. So where you are if you're 2 SD, 97.5. Okay. If you are here, right? If you're 1 SD, say suppose 70, you are 75. Where you are in the distribution, right? Here is 70%, right? And this is 15%. 15%, 85, 85%. So tell you where exactly you are. But of course, you're in the middle, of course, you are 50%, right? So you can do all the calculation. Is that clear? So that means that in the old days, right, you ask the professor, what is the mean in the class, what's the variance, then usually it's normal or more or less normal, then you know where you are already, right? What's the percentile you are, right? So I hope to give you the, I mean, we'll do the calculation, right, normal, but this is the rule, right? So essentially it means the following. Of course, usually people even don't talk about 1 SD and 3 SD. Usually talk about 2 SD rule, right? Actually, we'll do it in the upcoming future of the rest of semester. Actually, we use what we call the 2 SD rule. Things should be within 2 SD of the mean with 95% likely, right? So that means that highly likely that things should be within 2 SD. If things are beyond 2 SD, then you have some problem. Either you're very good or very bad. Okay, within 2 SD is very normal. Okay, later you figure out that this forms the basis of what we do in what we call estimation. We'll guess things by the mean and 2 SD. When we do hypothesis testing, we will talk about that is things are within 2 SD, will be normal. Outside 2 SD, will be abnormal. Okay, so, and this 2 SD rule is so commonly used, we'll use it the rest of the class. Of course, 2 SD is a rough thing, maybe sometimes 1.6, maybe sometimes 2 point something, but 2 SD is more or less that. If you forget everything about this class, 2 SD rule, I hope you remember. Mean plus minus 2 SD is where normal things are. Okay, you will see. Okay, but this is something that I hope stick in your mind, and that sometimes they call 3 sigma rule or 68, 95, 99 rule. Okay, this means that 3 SD is already covered 99%, right? So it's almost likely that if you are way beyond 3 SD or way below 3 SD, then there must be some issue there. Okay, okay, so that's something actually will be stick in your mind. Keep in mind that that is something very important. This is a the idea that we'll talk about the second half in the class. We'll keep using this 2SD, 3SD, right? Depends on how certain you want. Okay, but 1SD is too little, but usually we have the 2SD or 3SD. Okay, so don't worry about that. I mean, I just talk a little bit advanced of myself, but because later you learn, you can basically summarize the second half of course is basically 2SD. Okay, surprisingly. So this is the idea, right? The 3SD rule, 2SD rule. This is the idea. Okay, I hope it makes sense to you at the moment. Okay. And the next thing is because we use so many useful things, and then later we want to go back, right? We want to look at before we just have the number give probability, but we want to reverse it. Okay. Let me repeat what I said here, right? The set table is like this, right? This is 0 here. You give me number A here, okay? I give you this probability, right? It's f of A, right? Okay, this is a number here. I give a number A. I give you go back to there, right? I give you some number there. So the inverse is opposite. I give an area on the left-hand side. What is this number? Okay? If I give you 0.5, you know it's 0, right? If I give you positive infinity, that is 1. I give you negative infinity, 0. Okay? So shouldn't be too much surprising for you. I give you 2, will be 97.5. Right? Somewhat related. Okay? So how do you do that? Let's give you an example because that is something that we'll keep doing all the time. So give you this good example. What is the probability that Z is less than 0.95? Okay. How do you do that? Remember when I read the table, read the vertical column and look at number in the table, right? And find the probability. So we reverse it. We look at the table where the number closest to 0.95. Then we'll read the column and row again. Okay. Look at this. How can we read the 0.95? Go to the table. Oh, sorry, table is going up. Okay. Find where is closest to 0.95. Sorry. Yeah, it's here, right? Between these two numbers. Okay. So go back here is 1.645. Okay. 1.64, 1.65. Or you can take the middle if you don't like. Usually you take 1.64 or 1.65 or 1.645. Doesn't really matter to me. Anything between 1.64, 1.65, or anything you make it up between this number, two numbers will be fine. Our class is not very rigorous in that sense. As long as you put something, anything in between, we will be giving you pass. Okay. So that is how you read that table. Okay. So that's why 1.64 or 1.65 or 1.645. Okay. And same if you want to look at what's bigger than this. Okay. But the table only gives you the left-hand side. I'm asking the right-hand. I give you the right-hand side area. Right-hand side is 0.025. So the left-hand side is 0.975. 0.975 is actually 1.96. We showed you already, right? Because just to make sure you get it, I just draw it again because hopefully this is 0. This is Z. The area is given to me is this. I ask this number. This area is 0.025. Okay, and that means that this area is 0.975, right? Because they must add to 1. And look at the table, where it's closest 0.975. Okay, that will be 1.96. Okay, that's come from the 2 sigma rule, right? 2 sigma rule is 1.96. 1.96 is close to 2. Okay, so that's the 2 sigma rule comes from. Because 95% is in the middle. Okay, is that clear? Now, once we're done, we have to do some calculation, and then we'll give you some example for that. Okay. So far, we only tell you how to do the standard normal, right? So you can extend to any normal because, as I said, everything we observe is sometimes normal, but need not be mean 0, sigma 1, right? So you know how to calculate all the possible versions before we go to application. But this calculation is, I know the normal, right? Basically, this statement If you still remember, we can write X follow a normal distribution with mean 20 and variance 16, right? So that's what you do if you really want to write the notation. Okay. And how can we do that? Okay. This is the way that usually is the statistics textbook, right? And if variance is 16, standard deviation is 4. Okay. And you can see 16 is actually 1 SD below the mean 20, right? So that's why you have Z is -1 because it's 1 SD below it. So Z is what? Is how many SD from the mean. That's it. Let me repeat. Z is how many SD from mean. But of course, if you don't want to do it, you can do mechanically because every one of you come to here know how to do things mechanically. That's how you enter college, right? But what is Z? Remember, is how many SD away from mean. If less than negative, positive is more than. Okay. So you can do this is by subtracting 20 from the both hand side, right? That reserve inequality. You divide 4 on both hand side, they're the same thing. So this thing become the Z and this thing become -1, right? So it's just basically asking us how many SD different from the mean, 16, because 16 is 4 away from 20. Is that clear? So that's give you the answer, this guy. Let me show you again how to find this guy. Look at the table, -1, right? So the left-hand side area, 1, which is directly from the table, -1, this guy. See this here? Okay, so that's how we get this number. Okay. So this is the idea. You change X is 1 SD, same as this. So that's the table. I'll provide you this answer there. And similarly, if I want to have this, okay, mu is 20, sigma 16, right? You will ask why, what happened to this, right? It's normal. Okay. Again, the same idea. This is 1 SD above, right? And then you take 1 minus the answer we have is the answer we have because symmetric, right? 1 is less than -1, then more than 1, right? So that is -1, right? 1 minus this guy, because you can see the area here, same as the area there, symmetric, right? So just 1 minus that guy. Is that okay? I mean, just remember this 1 SD above the mean. Okay. Now here comes the very, very common question we do, right? Is X is between 16 and 24, right? And that is actually 1 SD below and above the mean, right? Actually, without that, you know it's going to be something around 70, right? This the empirical rule, 68, 95, 99, without calculation, 68, right? But let's do it, right? So you just basically between 1 and -1, right? So basically less than 1 and -1, so you already figured it out, right? Less than 1 is from this table. Less than 1 is this guy. Less than -1 is this guy, right? Why is the case? Is this difference of area, right? Because a table that, right? Maybe I just draw it here in case you don't really remember, right? So here, mean is 20, right? It's between 24 and 16. So this is area we want to know. Okay, this is X. But this is essentially same as the Z, and this becomes 0 here. This is -1, this is 1, because why? Because the SD is 4. Centimeters 4. So it's 1. This is 1 SD, right? 1 SD. This is also 1 SD, right? Because SD is 1. So this is the area. All right? The area of the middle will be the area from a smaller left-hand side. And this from a 1, you take the difference, right? Take the difference from 1 left and -1, and then the middle. This is the area less than 1, this area less than -1, the difference will be in between. Is that okay? Good. I mean, although I know this is something that you learn a lot when you are in the old days, but I hope that explains why you have this. Okay, because this guy, you can cut it here, the same area. So the difference give you the answer, right? The blue area, you flip it, then it's the difference. Is that okay? I know it looks trivial, but when you really work on an assignment, you figure out that you may not know very well. So please revisit this slide when you go back, because that slide, just to repeat, your assignment is asking you to do green thing again, and which I will also ask in the exam, right? Because this is something that I want you to know, and I don't talk about things that it's not important, right? I only keep, okay, remember, what I talk in the class is really minimal, necessary for you to go ahead, right? So you basically can't skip things. If you skip things, then you have a hole in your knowledge. So I already keep the minimum already. So you can't cut further, okay? Some of you say, why I cover so many things? But remember, I already covered the minimum that required, okay? So I'm not covering extra thing is not needed. Okay? So here is something that we are not using for the moment, but we will be seeing that very often soon. Okay? This is a very interesting property. Okay? And turn out to be only true for normal. Okay? If you're a bell curve, another bell curve, add together what you see. Okay? Let me write down here. So probably you will be surprised the result, because I also surprised by this result. Okay? So concept following. You are going to draw a number from the bell curve. Okay? The bell, of course, any bell is okay. Sigma square x, right? Some bell here. You pick a number from here. You close your eye, draw a number. Okay? From this. And now you also close your eye to draw a number. Okay? Maybe mu of y. Okay? Close your eye to draw two numbers from x and y. Okay? And add these two numbers together. Record it. Okay? Draw again, x and y, and add together. Okay? And what will you expect? You have x plus y. Okay? Your number add together, x plus y. Okay? Add together. What kind of shape you expect? Okay? Can be anything, right? Can be, I don't know, right? If you're this, so then I expect something like this happening, right? Suppose I should have two hills, right? Two valley, two model, right? Right? Or maybe I should have something like, I don't know, you expecting something like this? I don't know, something like that, right? So turn out, we're surprising. This is good. So be surprised by this. I was surprised. It's turned to be no. Well, interestingly, tell that you add the two bells together, it's still a bell. Amaze you, right? I always amazed by that. Why add the two bells bell? Yes, it's always a bell. Surprising. Okay? Not just you move, remember, right? We have the bell, you add things, you multiply things to a bell. But you add two bell, remains a bell. Right? It's something that blow your mind. I mean, I always surprised by why is the case, right? Then of course it explains why we call central limit theorem, everything become a bell, because you have a bell thing, combine everything to a bell. But that's why IQ, right? Remember I told you, right? If your everything, your brain, your gene, everything add together, everything's normal. At the end, many years, everything becomes still a bell, because everything is determined by many things as well, right? So this is the bell. Let's say very surprising. Okay, and of course, where is this location? Turn out to be just some of them. Okay, this plus this is the location. Not surprising. And the variance of this is just sigma x squared plus sigma y squared. Just if they're independent, okay? If x and y are independent, of course, if they're not independent, then we have some more things. But if there's just bell is independent draw, right? You close your eye and draw from X. You close your eye and draw from Y. It's the bell. You can imagine, right? This is how animal and human reproduce. Okay? X from your father, Y from your mother. You combine X plus Y is you. Hopefully it's right? Then this is still a bell. Right? Your DNA is like how you split, right? Half from your mom, half from your dad, right? Say randomly split, right? So that is what you have, you see, right? Is this surprising? I don't know, but it's always surprised me until now. No matter how many times I teach this, very surprising. I mean, because you expect something very weird shape, right? You don't expect, okay, bell plus bell, wasn't the same shape, still bell, right? It's like magic, okay? But this is the very interesting. The normal is such a magic thing. But I mean, if this blow your mind, I will blow your mind again. Second one is still blow your mind further. Look at the next one. The next one, the difference. So what do I mean by that? You will think adding 2 bell is still the bell. You subtract one from another. What do you see? Bell again. Very surprising, right? And even more surprising turn out to be, I would say, is if you have another bell is X minus Y or Y minus X. The mean is just mu X minus mu Y. What is the variance? The variance turns out to be same as this guy. That is the surprising part. The variance the same. So the shape is the same, just location different. You subtract 2 bell, the shape the same, just left and right is different. Something that always blow my mind means just you can't think, right? This is something that I think statistics, you have learned something is great. It's something that out of your mind, right? Something is like, you can prove it, but if you try to understand it, you still don't see why this is true, right? Of course, you can actually to prove it, there's some reason why it's right. But if you try to explain to people, right? You have 2 bell add together, you draw a thing, there's still a bell, right? So that is the reason exactly why something happened. Okay. I mean, of course, it's not too surprising in the sense that because remember your bell, you multiply a number, it's still a bell, right? So you multiply Y become -1, it's still a bell. So add together, it's still a bell. So it's not, you can understand why the case, right? Let me repeat. You have a bell, you multiply by -1, you flip it, it's still a bell curve, right? So that's why it's not that surprising to understand why add together, right? Because you just flip over 0, right? The bell is here, you flip over 0, it's the bell. So it's not super surprising if I try to explain to you. But still, you would think without thinking carefully why add and subtract to the bell, right? Probably you will now understand why, because the reason is because you multiply things, add things around to the bell. But let's explain why bell is so common, because no matter, as I told you, no matter how you torture it, how you move it around, it's still a bell. It's very resilient, right? It's very strong, persistent, right? No matter how much you squeeze it, destroy it, damage, and use the hammer to destroy and kill it, it's remaining a bell. Okay? There's something we strive for, right? No matter how the world is going to treat us, our cells remain innocent, remain pure, remain nice, remain good, right? So that's what we strive for. Anyway, so this is very nice part. Remember, 2 bell add together, still a bell. 2 bell different, is still a bell. Okay? Hope that explained. Now, this is the graph you can see here. I have 2 bell, add together is still a bell. Right? The blue and the red, the indigo, and then but the red is the blue one, right? And your red and still a little bit pale blue because of the blue. Okay. So hopefully explain why we have this kind of funny thing. Is that okay? Now sit back and relax because I talk about something that you don't never use it, but I just give you foundation. So if you get it, you get it. You don't get it, it's okay. Okay. What is this here? Okay. I will tell you some story. Hopefully it'll be useful. But so here we have a chi-square. What's chi? Chi is actually the typo. It should be x squared. Actually, in the old days, I don't know whether you know, when they print things, it's not print from printer, right? You print thing, you have to make some kind of physical mold, and you pick up the letter and then try to print thing out. And old days, people in those days they miss x and chi because they're so close to each other because it's a Greek letter. So that's why the chi-square. But what's chi-square? Okay, chi is x squared, and x squared x is actually z. It's standard normal square. What do I mean? You have bell and standard bell, and you square it. What you see, okay? And you can imagine the bell. The bell is like this, right? The bell 0, 1 is like this, right? Sigma is 1. This is a bell. Sigma square 1. This is the bell. Chi-square is like this guy. Okay, because everything is square, you can't have negative, right? So something like this would happen. This is 0. You can't go to 0. You only have 0, but the 0 is very unlikely. So basically, go like this guy. Okay. And probably you ask why we care about x squared, right? Are we crazy, right? What are we doing? Okay, why we care about this? And later you will see the chi-square is going to be a useful to model variance. Okay, later you will see, because you will later see the sample mean. We'll talk about sample mean, but sample mean is a random variable, and because collect data depending on who you collect, it's a random. We'll talk about in the second half, maybe it should be next week. We talk about the sample mean. We'll follow a bell curve in general if sample is large enough, and our variance, sample variance, will follow chi-square. So because we only need to know the mean and variance, and we can do all sorts of things. Okay, so this chi-square. And why you have one chi-square? Okay, because only one guy. Okay, one square. If you have many of them together, it's n chi-square. What do I mean by that? Let me say. So what is the chi-square? Chi-square is I bell, okay, 0. Okay, I pick a number there, I squared, it's chi-square of 1. If I have chi-square 2, means I draw a number, squared, I draw a number, squared, add together, chi-square 2. Chi-square 3 would be I draw a number, square, draw a number, square, draw a number, square, add all together. So chi-square k, or chi-square n, okay? And as I told you, if you draw n sample, the variance will follow the chi-square n minus 1. We'll talk about that later soon, but in the second half of our course. So that's why we need to model variance. We want to compare variance. That would be we need it, and ask why we care variance, right? Where is the risk? If you do finance, you care about risk. That's why we have that. You do quality control, you care about risk. That's what we need it. So it's often we have to do that. There's no way you can escape from this one. And all the things we do for the rest of the semester, we have this chi-square in the background. We don't do explicitly, but actually it can be used directly. But in our course, this will be in the background. Okay, we don't actually ask you to do the chi-square, but we will be use the next one. This is closely related to yours. Okay, a chi-square like this. If chi-square 1 like this, chi-square 3 look like this, chi-square 6 look like this. The more you add up, it's more like normal. If chi-square infinity is the bell, because you pick. Doesn't really matter. But anyway, the more important, as I want to conclude, is this guy. Okay, actually we almost finished the slide, but it's very happy. So basically we finished this week. So this is called the T distribution. Okay, and some history. This T distribution is also known as student T distribution. Okay, student is as you student. Okay, and you may ask, why is it with the student? Okay, the reason is that guy who invented this T distribution is not an academic. It's work in US, I think, very company. I think it's General Electric. And he is not allowed to write anything academic because he's employed by industry. So when he published his thing, he used a pen name called student. Just like when suppose you go out and work for industry and then you work on something, then you can publish things under your company name. Then use the name you call them yourself student. Okay. But what is this? This later we'll see is the following. It's a ratio, the fraction. The numerator is the bell. And the denominator, as I said, is chi-square m over m. Okay? And you ask, what are we doing? It's crazy. Why are we out of our head, right? So this is what? As I mentioned, we care about sample mean. Sample mean will be the numerator, normalized, right? And the below is the standard, is the sample variance of the sample mean. So when we do basically all 90% of our calculation in the second half of the class, rely on this one. I think 80%, at least 8 to 9% is like this one. Sample mean look like this student distribution, okay? And you may ask how the T looks like. So don't be surprised, or maybe you will not be surprised. This T, the student T, is very close to Bell. So that's why Bell is everywhere. This one is very close to Bell. Okay, if you look at the T table, when this thing is 30 or 40 or 50, if 200, more than 200, that is same. Okay, and what is this M? Actually the sample size. Okay, if you consider drawing samples more than 200, Bell is there. If less than 200, you don't have a normal. If it's something related to normal, it's a more, the shape looks like a better tail. So it's also have a bell shape, mean and median zero, symmetric, but a feather tail. So it's just a bell curve, but someone beat his head a little bit better or eat too much. Right? It's like tonight, some of you eat too much mooncake, become a student T here, right? The student is not, look like this, okay? The actual one, T infinity, which is the normal, will be the brown one. T infinity is like normal, okay? And if you have smaller sample, say the red one, the blue one, you can see the red one, the one sample or blue one, that would be much better. So basically, it's what you see when you collect a lot of sample, then your calculation will be very accurate because of you don't have much fat tail. Okay, so that's why the more sample you collect, the things you get more accurate, which will be very clear later. So remember the student T, the chi-square, we will cover later, don't worry. I just preview what we are doing. Okay? And, okay, since we can finish, why you don't? This last one, just preview, because we're not, don't worry, we'll use it later, so don't worry about that. I just mentioned it because for the sake of completeness. So the last one is called the F distribution. Turn out to be what? It's a ratio of 2 chi-square. You may ask, what's this? So if a chi-square of m, chi-square of n, you just divide by m over n. What does it do? This is comparing two variants. Later you will see, this is when you have two variants, we want to say they're the same or not. Why? Because we want to see whether stock A is more risky than stock B or not the case. Okay? And this is, we do it all the time to compare risk. Okay? And later also we learn what we call ANOVA, we learn regression, last two topics. And we compare whether we find a model as the model, whether the model is useful or not, we'll use this F test. Okay? So this F test, T test, we'll be using for the second half of our course. Okay? You don't have to worry about the chi-square thing, the minimum bell today. Okay? So although we have time, but I don't really want to start a new thing, but you will see the F look like this. Okay, F11 look like go down, and F51 look like this. Is a different shape. I'm not going to talk about those. Okay, but I take the last 3 minutes to remind you what we have covered so far today, mainly the normal. Okay, because I think that is important. So far today we talk about the bell curve. This is the notation we use. Okay, the mu and sigma squared, the bell curve. And the fun part is the bell curve. You multiply by constant plus a constant is still a bell curve. So you stretch it and squeeze it, add something, remain the bell. Okay, no matter you multiply or add, still a bell. And that means that you can always normalize to 0 to 1. And we learn how to use the C table, the Z table to calculate all the calculations we needed. And we also talk about the rule of thumb that come from the table. And also we learn how to, from the standard normal, can go back to the normal things. And we talk about adding 2 bell is still a bell. Subtracting 2 bell is still a bell. Okay. And then next is you have a bell into a square. It's called a chi-square. 1. If you have many squared together, the chi-square n. Okay, just need to know this. And t will be a normal over a chi-square thing, become a t. We will talk about this very soon. Okay, but and then you have 2 chi-square ratio. It's called the f. Okay, just know it because we'll be using it soon. At that time, we'll explain. So we are pretty much finished. We will talk about the next class. We'll talk about some Excel. That will conclude our whole chapter, and then the assignment, the quiz will be released after that. Okay, enjoy the holiday. Have a nice union with your family. I hope you have fun. For those who go to see your family and have midterm, good luck. I see you. If you anything more, please feel free to get it. I'm not going to walk around, but you can come and get one. Enjoy. Have a nice day.